everybody, it's Mr. Covey here, and today we're going to be talking about series. Okay, so you should have watched the video from Mrs. Lemke talking about sequences, and now we're going to talk about series. Series are actually way more important than BC calculus than sequences because they're more complicated, and we're going to learn a lot about series. Okay, so as a reminder, what's the difference between a sequence and a series? Well, as Ms. Lemke said, a sequence is an ordered list of numbers. A series is a sum of a sequence. It's not like a tongue twister. A series is a sum of a sequence. And what that means is if you have a sequence and you add up all of the terms, that is a series. So what is an infinite series? It's in the sum of an infinite sequence. Okay, so it's when you add up infinitely many terms. I know what you're thinking. If you add up infinitely many terms, you're just going to get infinity. Wrong, my friend. Wrong. Well, not wrong. Sometimes wrong, sometimes right. So how can you add up infinitely many things and not just get bigger and bigger and bigger? I'll give you a quick example. You might remember this from AATH, MAH. I'll give you a quick example. Let's say Benny has been, I don't know, selling bones to her friends. She's got like 100 grand. Okay. And she makes some purchases. She spends half her money. She spends $50,000. Then she spends half of what she has left, so she spends $25,000. Then she spends half of that. She spends $12,500. And she keeps spending half of her money over and over and over and over and over. Well, how many purchases is she making? I don't know where she's going, but how many purchases? She's making infinitely many purchases, if you ignore the dividing up pennies idea. She's making infinitely many purchases, but if she only ever spends half of her money, then in those infinitely many purchases, she only spends $100,000. So if you add up, in other words, all of these terms, there would be infinitely many of them. What would those infinitely many terms add up to? They'd actually just add up to 100,000. They wouldn't add up to infinity because the terms are getting smaller and smaller and smaller. And in fact, a phrase that we use a lot, which is kind of vague, but we'll talk about it a lot more, is those terms are getting small enough fast enough that when you add up infinitely many of them, you actually get a number, not infinity. That makes sense. We'll talk about this a lot. I know this is going to be confusing. Okay. So sometimes infinite series add up to a number, and sometimes they add up to infinity. When they add up to a number, we call that convergent. Series convergent. When they add up to infinity, we call this divergent. We call that series divergent. Okay. To understand a little more about how you can think about series being convergent or divergent, though, we have to introduce one other term, which is a partial sum. Okay. So let's go back to our Benny example. Let's say we have this sequence, and if we add them all together, we call that a series. If we want to talk about a partial sum, it means we're not going to sum up infinitely many of them. We just want to sum up some of them. So you have something called a first partial sum, which is just the first term. You have the second partial sum, which means sum up the first two terms. You have the third partial sum, which means what do you get when you sum up the first three terms, and so on. Okay? So in this case, the first partial sum would be 50,000. The second partial sum would be 75,000. The third partial sum would be 87,500. Fourth part. Okay. So you with me so far? I know it's a lot of vocab. I know this is confusing. Trust me. So the way that we say a series, an infinite series, converges is we look at that infinite series. Okay, notice that we have a little infinity on top there. There's infinitely many terms. And we look at the sequence of partial sums. In other words, we find these partial sums, and we think about these as being the terms of a sequence. And the reason we do that is because we understand sequences well. I can look at this sequence, and I can ask myself, is this sequence converging? Okay, and you could do some more partial sums if you wanted, but you'd see that this sequence is converging to 100,000, this sequence of partial sums. Again, these are called partial sums, that's why it's called a sequence of partial sums. Since the sequence of partial sums converges, in this case, to 100,000, we say that the infinite series converges to 100,000. So 50,000 plus 25,000 plus 12,500 plus blah, 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 infinitely many terms all added together equals 100,000, because that sequence of partial sums converges to 100,000. Okay, here is that all written out. Sorry. There we go. There's that all written out in fancy language. You have an infinite series, you look at the sequence of partial sums, and that converges to a number, then the infinite series converges to a number. And if it diverges, then the infinite series diverges. Okay. Most important thing right here. A bunch of people last year got confused. This is what we mean by whether an infinite series converges or diverges. This is not how you actually test if an infinite series converges or diverges. We're going to learn 20 ways to tell if an infinite series converges or diverges. It's going to be great. You're going to love it. Mostly in the spring we'll learn that. But this is what we mean by the concept. So this sequence of partial sums is an idea. It's not a calculation that we're going to do very often. The first test we're going to talk about how to test if an infinite series converges or diverges is something you learned back in AATH. Okay, and it's specifically if you're looking at an infinite series that is geometric. Okay, you might remember the infinite series have a common ratio. So if you look at this, sorry, geometric series have a common ratio. So if you look at this series, it is geometric because you're multiplying by 1/10 over and over and over, right? To get from one term to the next, you're just multiplying by 1/10. That's the constant ratio. So in this case, we'd have a geometric series with a constant ratio of 1/10. Again, why am I calling this a series rather than a sequence? Because of those little plus signs. And why am I calling it an infinite series? Because of that little dot. So it's saying we're adding up infinitely many things. So here is an infinite geometric series. And it's easy to tell whether an infinite geometric series converges or diverges. The idea here is if the terms are getting smaller, then the geometric series, infinite geometric series is going to converge. If the terms are getting bigger, then obviously that infinite series is going to diverge. Okay, so here the terms are clearly getting smaller. This is a geometric series because it has a common ratio. So this geometric series is going to converge. Okay, all you need to think about is the R. Okay, so skip forward with me a little bit. We're going to come back to that in a second. But if you're looking at a geometric series and you have a common ratio of 1, the series is going to diverge. Okay, and that's kind of obvious. If you have a geometric series, and let's say your first term is 5, and then your second term is 5 times 1, and your third term is times 1 times 1, and you add up infinitely many, obviously that's going to be infinity. So that infinite series is going to diverge. If your common ratio for your infinite geometric series, you might remember this again from AATH, is between -1 and 1, then your infinite geometric series converges. Okay, and there's going to be a nifty formula for that. We'll talk about that in a second. If your R, absolute value of R, is bigger than 1, then again, of course, your infinite series diverges. What this means is your numbers are getting bigger and bigger. 5 plus, let's say we have R equals 2, plus 10, plus 20, plus 40, plus 8. If I add up infinitely many numbers and they're getting bigger and bigger, of course, that's just going to diverge. It's just going to go to infinity. There's no way I'm going to add up 5 plus 10 plus 20 plus 40 plus 80 plus and get like 64. It doesn't make any sense, right? You're going to go up to infinity. That infinite series is going to diverge because it's geometric and the common ratio is bigger than 1. Okay, so when you have an R that's between -1 and 1 in your geometric series, it's going to converge to a number, and there's a formula to calculate what that number is. Okay, you might remember this formula. It is this. where a sub 1 is the first term in the series, and r is the common ratio, then the sum of infinitely many terms in that geometric series is just the first term divided by 1 minus the common ratio. Okay? So to jump back really quick, skip past Benny there, for this infinite geometric series, since r is a tenth, our formula is going to apply. The first term is 3/10, 1 minus the common ratio. This is what those infinitely many terms are going to add up to. And if you type that in, calculate it out, you get a third. Okay? And so in this case, 3/10 plus 300s plus 3,000s plus 3 10,000s plus 300,000s plus 3 millions, blah, 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 adds up to a third. Okay? I'm going to do a quick derivation of that formula. In other words, I'm going to explain why that is the formula and how it works. Again, I'm never going to ask you to do this again, but the more you understand about it, the more helpful it is. You can think about an infinite geometric series as being a first term plus the first term times the common ratio plus the first term times the common ratio times the common ratio again, blah, blah, blah. So you can think about it like this. And here I'm doing it for n terms, so for any number of terms. We have a formula like this. Okay. And I'm going to do a quick derivation here. So let's multiply each term by r, and then we're going to kind of line them up here. Okay, so I took the green guy, I multiplied every term by r, I got the red guy. Now I'm going to take green guy and subtract red guy. Okay. When I do that, I get this on the left side, and on the right side, you see, oh look, if I subtract those, then like boom, 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 I get a sub 1 minus, there's this annoying thing left over here. That's fine though. Again, I'm trying to find a formula for s sub n, for the sum of n terms. So what I'm going to do here is factor out a GCF of s sub n. I'm going to get 1 minus r equals a sub 1 minus a sub 1 r to the n. Again, I'm deriving a formula here. The sum of the first n terms of a geometric series is therefore a sub 1 minus a sub 1 r to the n divided by 1 minus r. And there we go. I know what you're thinking. That's a little more complicated than this one. And that's because, remember, we're trying not to find the sum of n terms in in a geometric series. We're trying to find the sum of an infinite geometric series with infinitely many terms. So if we think about it as a limit, and we let n go to infinity, well, if n goes to infinity, this chunk will go to 0 as long as r is between -1 and 1, right? Because if r is 3, then 3 to the infinity, then it's going to blow up. But if r is a half, then a half to the infinity, if we evaluate that limit, that term is going to go away, and we're going to be left with this guy. Okay, so here's our formula. Again, I can't stress enough, this formula only works if r is between -1 and 1. You can try and use it other times, but it literally tells you nothing. Okay, it tells you inaccurate information. Just to illustrate that point further, let's say you looked at this infinite geometric series and you got excited and you remembered your formula and you just wanted to jump right into that formula. You're like, oh, I'm going to figure out what that adds up to. I'm going to do the first term divided by 1 minus the common ratio. You get that this infinitely many terms add up to -5. Obviously, 5 plus 10 plus 20 plus 4 doesn't add up to -5. That makes absolutely no sense. And that's because r in this case is 2. R 2 is not between -1 and 1. Therefore, the formula doesn't apply. Okay. So, big summary. Okay. So here's the big summary. If a series is geometric, again, that means there's a common ratio between the terms. There's a number you're multiplying by to get from one term to the next. And that number, the absolute value of it, is less than 1. Then that infinite series converges. And in fact, there's a formula to figure out what it converges to. Here's the formula. First term divided by 1 minus r. If the absolute value of that common ratio is greater than or equal to 1, that infinite series diverges. Okay, I really don't want to do this since this is BC, but I I'm feeling there's some people that are a little confused right now because of the forgetting what a geometric sequence is, ATH and MAH. So we'll go over this very briefly. There are two types of sequences you learned about, arithmetic and geometric. Arithmetic sequences have a common difference. Here is an infinite arithmetic series. The common difference is 2. To go between the terms, you are adding something every time. Okay, so 3, 5, 7, 9, those are all plus 2 from each other. If you have an infinite arithmetic series, it always diverges. That's why we haven't talked about this before. Geometric series have a common ratio. So to go between the terms, you're not adding something, you're multiplying by something. Okay? Infinite geometric series have a chance of converging or diverging. See the previous slide, we were just talking about that. Infinite arithmetic series always diverge, so we're never going to talk about them again. They're boring. If you have an arithmetic series, an infinite one, it's going to diverge. Okay. I want to do 3 quick examples, and then we're out of here. Okay, I'm gonna actually have you guys do these. So the directions should I say determine if the infinite series below converges or diverges. If they converge, determine what they converge to. What number do they converge to? Okay, so there's 3 examples here. I'd like you to jot those down and give them a try. One of them is a trick, so don't spend too long if you get stuck on one. But give it a try. Pause the video, and we'll chat. Pause the video. Pause the video. Thank you. Okay, I got my answers here. So this first series was infinite, again, because of those 3 dots. It's a series because I'm adding terms and a sequence. It was geometric, sweet. Ooh, but R was 4/3, so that infinite series diverged. Second one, again, oh cool, geometric series. R was a half. The absolute value of R is between -1 and 1. Excuse me, the absolute value of R is less than 1. Therefore, this infinite series converged, and in fact, I can use my nifty little formula to figure out that it converges to 6. Okay, again, that makes sense if you like 3 plus 3 halves plus 9/4 and keep going on. Oh, I'm sorry, I made a typo there. Come on, Mr. Covey. Mrs. Lemke wouldn't do that. She doesn't make typos. Sorry, if you could change that to a 3. Come on, Mr. Covey. All right, so then A, it's geometric, R is 1/2, it converges using our formula to 6. Okay, if you looked at this last infinite series, 1 plus a half plus a third plus a fourth seems pretty simple. It is not geometric, though. There's not something you are multiplying by to get between these terms, because 1 times a half is a half, but a half times a half is a 4. Doesn't work. If you want to take a guess, this is a very special series called the harmonic series, and it actually diverges, but you don't know that yet, and you won't know that for a while, which is kind of weird because it kind of looks like it converges. Anyway, for our purposes right now, if you come across a infinite series that's not geometric, well, we don't know. That's what we're going to learn. One of the big things we're going to learn in BC Calculus is how to deal with series that are not geometric. Again, I'll say this one more time. These 2 problems were literally problems you did in AATH. I just wanted to remind you about how to deal with them. Problems like this, next few weeks, and then in the spring we'll learn more about those. Cool. I know this is a confusing topic. We'll talk about it lots. Don't worry. Thanks for watching, guys.